So good afternoon, everyone. My name is Ismael. I am the founder of Lagrange Labs. So broadly, we build proof constructions that allow us to construct very large batch proofs concurrently with MapReduce style computation over large subsets of a commitment. And so my talk today, we're going to cover applying batch proofs and vector commitments to blockchain applications. We're going to start by discussing some work that our team recently did with rec proofs using recursion. And then we're going to discuss some other work that our team has recently proposed involving the use of folding schemes to extend this to anything that really supports recursion or an abstraction of recursion such as folding. So what are rec proofs? Rec proofs is a new paper our team presented at Stanford Blockchain Conference this summer that is a vector commitment that is designed for concurrently proving both batched set inclusion and dynamic MapReduce style computations. And so to start with, let's think about the anatomy of a Merkle tree, right? A commitment to an ordered sequence of values, likely a review for everyone here, that's created through a recursive concatenation and hashing of adjacent values. And so when you want to prove inclusion in a Merkle tree, very simply, you would take some leaf element, let's say in this situation, A5, and you would take the adjacent leaf value and the adjacent branch values, and you would reconstruct the path by recursively concatenating and hashing. And so what if you wanted to update the membership proof? For example, the set that you are computing over changes. Well, in this situation, the time to update a membership proof is logarithmic with respect to the size of the tree. Now, what about a batch proof? Let's say you want to have a batch proof that opens k arbitrary elements simultaneously. Naive approach to a batch proof would involve just taking the portions of the path that overlap and constructing the inclusion proof from there. But the complexity now comes when you want to create a snark for that batch proof. If the set that you are computing over, or the subset, changes, this would necessitate a recomputation of the entire batch proof in a snark from scratch. Which, if you think about continually updating data structures, which is what blockchains are, this is not a very effective paradigm. So the imperative to recompute something from scratch, which the main benefit being smaller proof size, is not a very effective design when you think about the application of this to things that have entropy in the underlying set or subset you're computing over. And so this is where rec proofs is designed to be a solution to this issue. So rec proofs is a new form of batch proof that's updatable in logarithmic time and can be used to verify both the inclusion of some subset of elements within a commitment, as well as the result of a data parallel computation, something like MapReduce, SQL, or RDD, that is done on top of this subset. And the key principle here is that it is now updatable in logarithmic time thanks to an advancement our team put forward called canonical hashing. So what canonical hashing does is it establishes a proof of the subtree rooted at every branch node. And so by taking a proof of the node subset contained below and the proof of the subtree rooted at every branch, in the event that the set or the subset that you're computing over changes, you only have to alter the path corresponding to where there has been a change in the node subset or the subtrees rooted there. And what this gives you is a very flexible primitive for batch proofs. And so we can extend this concept of the node subset not just to prove inclusion, but to prove an arbitrary computation over that subset. In the style of the work that we're doing, and we're talking about, let's say, a binary composition of proofs, we typically are working with data parallel computation, things like MapReduce, Spark, RDD, and SQL, that we can prove have been correctly executed over the subtrees rooted at every position. And so what this is very good at is large-scale computations over data structures that have low entropy, because you only have to pay for the complexity of updates rather than the complexities of recomputation. And so let's look at a very simple example of where this can be applied in the blockchain context, kind of anchoring back to the title of this talk. So let's say you want to compute the volatility of an asset over some range k of blocks. You will have to initially expend computation proportionate to the range k. But it's a blockchain, data changes, there's new blocks. And so a new block comes in. And you want to update or use your previous proof such that it is now relevant to the new range. Let's say from block B minus 1 or B plus 1 to B minus K plus 1. If you were using a naive approach to snarks, you would have to recompute from scratch this entire batch proof, which is not necessarily a very effective paradigm. So with rec proofs, all you have to do is expend computation proportionate to the update. So in this case, it would be one block of the range K. And so this is very flexible when you talk about long-running computations that necessitate an iterative update for whenever new data is added. Think price feeds, volatility, user rewards for airdrops, etc. And so what are the actual performance benefits of doing an update as compared to a recomputation? So in the first paper that our team put out at SBC, we showed the improvement in speed of about 135x compared to recomputation using naive batch proof approaches. Since this is fully parallelizable, we are able to get speed improvements up to 10, 11x by going embarrassingly parallel on how we're doing our proving. And because we're using a PCD-based approach, the proof size and the verification time are much smaller as well. Now, we're going to talk about some new work that our team's recently done, and this has been led by Nicola Guiley on our team, which is taking folding and using rec proofs with folding, and our ZK MapReduce stack broadly with folding. So if we think about the proof systems and the proof constructions we've discussed, it's important to recognize that the arity of the composition of proofs has to be the same as the arity of the data structure that's being proved over. So if you're talking about a binary tree that you're computing over, or a binary Merkle tree, you'll need to be able to compose proofs such that they have a branching factor of 2. If you're using an MPT tree, you need to support an arity of 16. And so this means that when we talk about folding and we talk about a lot of the current approaches to folding, you need to think about being able to do this with a higher arity than the linear folding that we're more familiar with. So if we look at the public implementations of Nova available today, they only support IVC-based folding, where you sequentially prove the execution of every step and then you compose them together. There's a single running instance that's used as input for the next proof. The issue with this is obviously this doesn't support the types of constructions that we've been discussing up until this point. And so what we need to do is to take the public implementations of Nova, and we need to upgrade those to move from an IVC-based construction to a PCD-based construction, such that the computation can be done in parallel, and then the computation can be later aggregated. And so what we're going to talk about is some work that Nicola Guiley and our team did that takes the F prime circuit used in Nova and turns into what we like to call takes the F circuit used in Nova and turns into what we like to call F prime here, that lets us do ZK MapReduce and rec proofs in a parallel iteration and parallel computation format. And so what we do here is we take our augmented F prime circuit, and then we take two running instances, left and right, and we fold these into each other. And on top of that, we can apply a reduce function that outputs the result of the two of those. We can change the consistency checks within the F prime to be able to support both a consistency check on the left fold and the right fold. And we can take the merge step, and we can ensure that that can actually accurately apply computation over the data that's included within both the left and the right fold. So by doing both the hash consistency checks in parallel, and then folding those both into a given instance, we're able to take the linear folding and we're able to upgrade that to now support a PCD style of proof composition. And what we can additionally do is we take both of the outputs from each of the parallel running instances, and we can combine those into a single running instance. And so the main takeaway of this is you can now take the work that's been done by turning the public implementations of Nova into something that supports a PCD-based proof construction, and you can upstream that into all of the other implementations of Nova that we see publicly available. And so the applications of this are typically in trying to compute things over large subsets of a commitment that you want to then iteratively update or change. So if you're thinking about, let's say, a roll-up or a coprocessor or a booster roll-up, and you want to iteratively and regularly compute over a large subset of on-chain state, what you will typically have to do is run a large number of MPT proofs or inclusion proofs over the underlying data. This is not very effective if these are frequently computed over sections of memory, because you'll, with every proof you compute, have to deal with the snark unfriendly encodings and the snark unfriendly hash functions. And so what you can do is you can take the portion of a structure corresponding to a certain part of memory in the chain, and you can prove that that's equivalent to a new structure that's designed to be more friendly to whatever the secondary proving system is that's going to be used for the coprocessor or the booster rollup or the VM extension or whatever the secondary application is. And so by being able to prove that equivalence, you're able to take the formally unfriendly structure and then use that, or only use the friendly rendering of that. Another use case that our team talks a lot about is something called updatable BLS aggregations. So the updatable BLS aggregations, we are able to take a signer subset of some commitment that's contained in some commitment, and we're able to aggregate the public keys over that. And when we think about this public key aggregation, like think you were trying to prove a consensus or you're trying to prove some eigenlayer AVS, you will typically have to expend computation proportionate to the number of keys that are being aggregated, a linear time operation. But if the entropy in the signer set or the subset is low enough, you're able to then reuse all of the aggregation between successive runs with rec proofs. And this gives you a very flexible primitive when you're trying to prove computation over something, in this case a set of BLS keys, that doesn't have high changes between every iterative run of iterative computation of the proof. So for those of you who are interested in digging into a little bit more detail on our work here, there are two resources I would refer you to. The first is the rec proofs paper that our team presented at SPC this summer, and the second is the work from Nicola on our team that recently took the IBC implementation of Nova and upgraded that to support PCD-based folding. And for those of you who would rather just dig into the code, we also have the commits for this public so that everyone can take a look at this and hopefully build and enhance it. Thank you, everyone.
Thank you, Ismael, for your talk a lot. We have a few minutes for the Q&A.
Hi, thank you very much. I'm not an expert on this topic, but I've seen two other examples of where data structures are kind of used to improve how we prove things about inclusion. So we have the Verkle tree stuff, where we use the vector commitments. And then we have people using Merkle mountain ranges. But tell me how this fits in and how is this pushing things forward?
Yeah, so data structures are a primitive in computation. And that extends past the applications of data structures for computation in crypto or for how we're structuring data in crypto. So we see data structures used in computation going all the way back to compiler design. And so the work with Verkle trees is designing a new data structure that leverages a vector commitment as part of its underlying design. With this work, you take an existing data structure, in this case, any Merkle tree or any type of form of a Merkle tree, and you're able to structure computation on top of that with a batch proof. So it's very much, this work would potentially overlap with any new data structure that you're designing. So if you wanted to use your Merkle mountain range for something, or if you want to use your Verkle tree for something, you can do that, and you can likely use some of the same principles of rec proofs on top of that. So this is a way of proving inclusion. Merkle mountain ranges and Verkle trees, to your point, are separate data structures that one would potentially wish to prove inclusion within. The gentleman in the front.
Yes, thank you very much. I love your presentation. And a question is, if let's say you actually introduce two works, and I'm wondering the second one, the new one, if this has been published or not, if I want to set your paper or something like that.
Yeah, rec proofs is, we have a work in progress draft up at that link, but we'll be submitting it to conferences soon.
Okay, thank you very much.
Great, we are over the Q&A time. So thank you so much.
Thank you, everyone.